Welcome back, or welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled Rammed Earth. Rammed earth is a technique for constructing foundations, floors, and walls using compacted natural raw materials such as earth, chalk, lime, or gravel. It is an ancient method that has been revived recently as a sustainable building method. Under its French name, pisé, it is also a material for sculptures, usually small and made in molds. It has been especially used in Central Asia and Tibetan art, and sometimes in China. Edifices formed of rammed earth are found on every continent except Antarctica, in a range of environments including temperate, wet, semi-arid, desert, montane, and tropical regions. The availability of suitable soil and a building design appropriate for local climatic conditions are two factors that make its use favorable. The French term pisé de terre or terre pisée was sometimes used in English for architectural uses, especially in the 19th century. Making rammed earth involves compacting a damp mixture of subsoil that has suitable proportions of sand, gravel, clay, silt, and stabilizer, if any, into a formwork and externally supported frame or mold. Historically, additives such as lime was used to stabilize it. Soil mix is poured into the framework to a depth of 10 to 25 centimeters and then compacted to approximately 50% of its original volume. The soil is compacted iteratively in batches or courses so as to gradually erect the wall up to the top of the formwork. Tamping was historically manual with a long ramming pole by hand, but modern construction systems can employ pneumatically powered tampers. After a wall is complete, it is sufficiently strong to immediately remove the formwork. This is necessary if a surface texture is to be applied, e.g., by wire brushing, carving, or mold impression, because the walls become too hard to work after approximately 1 hour. The compression strength of rammed earth increases as it cures. Cement stabilized rammed earth is cured for a minimum period of 28 days. In modern rammed earth buildings, the walls are constructed on top of conventional footings or a reinforced concrete slab base. The construction of an entire wall begins with a temporary frame, the formwork, which is usually made of wood or plywood, as a mold for a desired shape and dimensions of each section of wall. The form must be durable and well braced, and the two opposing faces must be clamped together to prevent bulging or deformation caused by the large compressing forces. Formwork plays an important role in building rammed earth walls. Historically, wooden planks tied using rope were used to build walls. Modern builders use plywood and or steel to build formwork. The compressive strength of rammed earth is dictated by factors such as soil type, particle size distribution, amount of compaction, moisture content of the mix, and type or amount of stabilizer used. Well-produced cement stabilized rammed earth walls can be anywhere between 5 and 20 megapascals. Higher compressive strength might require more cement, but addition of more cement can affect the permeability of the walls. Indeed, properly constructed rammed earth endures for thousands of years, as many ancient structures that are still standing around the world demonstrate. Rammed earth walls are reinforced with rebars in areas of high seismic activity. Adding cement to soil mixtures low in clay can also increase the load bearing capacity of rammed earth edifices. The United States Department of Agriculture observed in 1925 that rammed earth structures endure indefinitely and can be constructed for less than two-thirds of the cost of standard frame houses. Rammed earth works require at least one skilled person for quality control. All other workers can be unskilled or semi-skilled. One significant benefit of rammed earth is its high thermal mass. Like brick or concrete, it absorbs heat during the day and releases heat at night. This action moderates daily temperature variations and reduces the need for air conditioning and heating. In colder climates, rammed earth walls can be insulated by inserting insulation such as styrofoam or rigid fiberglass panels within internal and external layers of rammed earth. Depending on the type and content of binder, it must also be protected from heavy rain and insulated with vapor barriers. Rammed earth can effectively regulate humidity if unclad walls containing clay are exposed to an internal space. Humidity is regulated between 40% and 60%. The material mass and clay content of rammed earth allows an edifice to breathe more than concrete edifices. This avoids problems of condensation and prevents significant loss of heat. Rammed earth walls have the color and texture of natural earth. Moisture impermeable finishes, such as cement render, are not used by some people because they impair the ability of a wall to desorb moisture, which quality is necessary to preserve its strength. Blemishes can be repaired using the soil mixture as a plaster and sanded smooth. The thickness varies widely based on region and code. It can be as little as 6 inches for non-load bearing walls and up to 24 inches for load bearing walls. The thickness and density of rammed earth walls make them suitable for soundproofing. They are also inherently fireproof, resistant to termite damage, and non-toxic. Edifices of rammed earth are more sustainable and environmentally friendly than other building techniques that use more cement and other chemicals. Because rammed earth edifices use locally available materials, they usually have low embodied energy and generate very little waste. The soils used are typically subsoil, which conserve the topsoil for agriculture. When the soil excavated in preparation for a foundation can be used, the cost and energy consumption of transportation are minimal. Rammed earth is probably the least environmentally detrimental construction material and technique that is readily and commercially available today to construct solid edifices. Rammed earth has potentially low manufacturing impact, contingent on the amount of cement and the amount that is locally sourced. It is often quarried aggregates rather than earth. Rammed earth can contribute to the overall energy efficiency of edifices. The density, thickness, and thermal conductivity of rammed earth render it an especially suitable material for passive solar heating. Warmth requires almost 12 hours to be conducted through a wall 35 centimeters thick. Mixing cement with the soil can counteract sustainable benefits, such as low embodied energy, because manufacture of the cement itself creates 1.25 tons of carbon dioxide per ton of cement produced. Although it has low greenhouse gas emissions in theory, transportation and the production of cement can add significantly to the overall emissions of modern rammed earth construction. The most basic kind of traditional rammed earth has very low greenhouse gas emissions, but the more engineered and processed variant of rammed earth has the potential for significant emissions. Evidence of ancient use of rammed earth has been found in Neolithic archaeological sites, such as those of the Fertile Crescent, dating to the ninth to 7th millennium BC, and of the Yangshao and Longshan cultures in China, dating to 5000 BCE. By 2000 BCE, rammed earth architectural techniques were commonly used for walls and foundations in China. In the 1800s, rammed earth was popularized in the United States by the book Rural Economy by S. W. Johnson. The technique was used to construct the Burrow House Plantation and the Church of the Holy Cross in Statesburg, South Carolina, both being National Historic Landmarks. Constructed in 1821, the Burrow House Plantation Complex contains the oldest and largest collection of high-style pieds-de-terre, rammed earth, buildings in the United States. 6 of the 27 dependencies and portions of the main house were constructed using this ancient technique, which was introduced to this country in 1806 through the book Rural Economy by S. W. Johnson. An outstanding example of a rammed earth edifice in Canada is St. Thomas Anglican Church in Shanty Bay, Ontario, erected between 1838 and 1841. From the 1920s through the 1940s, rammed earth construction in the U.S. was studied. South Dakota State College extensively researched and constructed almost 100 weathering walls of rammed earth. For over 30 years, the college investigated the use of paints and plasters in relation to colloids in soil. In 1943, Clemson Agricultural College of South Carolina published the results of their research of rammed earth in a pamphlet titled Rammed Earth Building Construction. In 1936, on a homestead near Gardendale, Alabama, the United States Department of Agriculture constructed experimental rammed earth edifices with architect Thomas Hibben. The houses were inexpensively constructed and were sold to the public along with sufficient land for gardens and small plots for livestock. The project was successful, providing homes to low-income families. The U.S. Agency for International Development is working with developing countries to improve the engineering of rammed earth houses. It also financed the authorship of the Handbook of Rammed Earth by Texas A&M University and the Texas Transportation Institute. Interest in rammed earth declined after World War II, when the cost of modern construction materials decreased. Rammed earth is considered substandard and is opposed by many contractors, engineers, and tradesmen. The prevailing perception that such materials and techniques perform poorly in regions prone to earthquakes has prevented their use in much of the world. In Chile, for example, rammed earth edifices normally cannot be conventionally insured against damage or even be approved by the government. A notable example of 21st century use of rammed earth is the facade of the NK Desert Cultural Center in southern British Columbia, Canada. As of 2014, it is the longest rammed earth wall in North America. Rammed earth construction was both practically and ideologically important during the rapid construction of the Daqing oil field and the related development of Daqing. The Daqing spirit represented deep personal commitment in pursuing national goals, self-sufficient and frugal living, and urban-rural integrated land use. Daqing's urban-rural landscape was said to embody the ideal communist society described by Karl Marx because it eliminated 1, the gap between town and country, 2, the gap between workers and peasants, and 3, the gap between manual and mental labor. Drawing on the Daqing experience, China encouraged rammed earth construction in the mid-1960s. Starting in 1964, Mao Zedong advocated for a mass design revolution movement. In the context of the Sino Soviet split, Mao urged that planners should avoid the use of Soviet style prefabricated materials and instead embrace the proletarian spirit of on site construction using rammed earth. The Communist Party promoted the use of rammed earth construction as a low cost method which was indigenous to China and required little technical skill. During the Third Front campaign to develop strategic industries in China's rugged interior to prepare for potential invasion by the United States or Soviet Union, Planning Commission Director Li Fuchun told leaders to make do with what was available, including building rammed earth housing so that more resources could be directed to production. This policy came to be expressed through the slogan, "First build the factory and afterward housing." Adobe is a building material made from earth and organic materials. Adobe is Spanish for mud brick. In some English speaking regions of Spanish heritage, such as the southwestern United States, the term is used to refer to any kind of earthen construction or various architectural styles like Pueblo revival or territorial revival. Most adobe buildings are similar in appearance to cob and rammed earth buildings. Adobe is among the earliest building materials and is used throughout the world. Adobe architecture has been dated to before 5100 BC. Adobe bricks are rectangular prisms, small enough that they can quickly air dry individually without cracking. They can be subsequently assembled with the application of adobe mud to bond the individual bricks into a structure. There is no standard size, with substantial variations over the years and in different regions. In some areas, a popular size measured 8 by 4 by 12 inches, weighing about 25 pounds. In other contexts, the size is 10 by 4 by 14 inches, weighing about 35 pounds. The maximum sizes can reach up to 100 pounds. Above this weight, it becomes difficult to move the pieces, and it is preferred to ram the mud in situ, resulting in a different typology known as rammed earth. In dry climates, adobe structures are extremely durable and account for some of the oldest existing buildings in the world. Adobe buildings offer significant advantages due to their greater thermal mass, but they are known to be particularly susceptible to earthquake damage if they are not reinforced. Cases where adobe structures were widely damaged during earthquakes include the 1976 Guatemala earthquake, the 2003 BAM earthquake, and the 2010 Chile earthquake. Buildings made of sun-dried earth are common throughout the world: Middle East, Western Asia, North Africa, West Africa, South America, Southwestern North America, Southwestern and Eastern Europe. Adobe had been in use by indigenous peoples of the Americas and the southwestern United States, Mesoamerica, and the Andes for several thousand years. Puebloan peoples built their adobe structures with hands full or baskets full of adobe until the Spanish introduced them to making bricks. Adobe bricks were used in Spain from the late Bronze and Iron Ages, 8th century BC onwards. Its wide use can be attributed to its simplicity of design and manufacture and economics. The word adobe has existed for around 4,000 years, with relatively little change in either pronunciation or meaning. The word can be traced from the Middle Egyptian, circa 2000 BC, for mud brick. Middle Egyptian evolved into Late Egyptian, and finally to Coptic, circa 600 BC, where it appeared as toba. This was adopted into Arabic as atubu, with the definite article al attached to the root tuba. This was assimilated into the Old Spanish language as adobe, probably via Mozarabic. English borrowed the word from Spanish in the early 18th century, still referring to mud brick construction. In modern English usage, the term adobe has come to include a style of architecture popular in the desert climates of North America, especially in New Mexico, regardless of the construction method. An adobe brick is a composite material made of earth mixed with water and an organic material such as straw or dung. The soil composition typically contains sand, silt, and clay. Straw is useful in binding the brick together and allowing the brick to dry evenly, thereby preventing cracking due to uneven shrinkage rates through the brick. Dung offers the same advantage. The most desirable soil texture for producing the mud of adobe is 15% clay, 10 to 30% silt, and 55 to 75% fine sand. Another source quotes 15 to 25% clay and the remainder sand and coarser particles up to cobbles 50 to 250 millimeters, with no deleterious effect. Modern adobe is stabilized with either emulsified asphalt or Portland cement up to 10% by weight. No more than half the clay content should be expansive clays, with remainder non-expansive illite or kaolinite. Too much expansive clay results in uneven drying through the brick, resulting in cracking, while too much kaolinite will make a weak brick. Typically, the soils of the southwest United States, where such construction has been widely used, are an adequate composition. Adobe walls are load-bearing, i.e., they carry their own weight into the foundation rather than by another structure. Hence, the adobe must have sufficient compressive strength. In the United States, most building codes call for a minimum compressive strength of 2.07 newtons per millimeter squared for the adobe block. Adobe construction should be designed so as to avoid lateral structural loads that would cause bending loads. The building codes require the building to sustain a 1 gram lateral acceleration earthquake load. Such an acceleration will cause lateral loads on the walls, resulting in shear and bending and inducing tensile stresses. To withstand such loads, the code typically calls for a tensile modulus of rupture strength of at least 0.345 newtons per millimeter squared for the finished block. In addition to being an inexpensive material with a small resource cost, adobe can serve as a significant heat reservoir due to the thermal properties inherent in the massive walls typical in adobe construction. In climates typified by hot days and cool nights, the high thermal mass of adobe mediates the high and low temperatures of the day, moderating the temperature of the living space. The massive walls require a large and relatively long input of heat from the sun, radiation, and from the surrounding air, convection, before they warm through to the interior. After the sun sets and the temperature drops, the warm wall will continue to transfer heat to the interior for several hours due to the time lag effect. Thus, a well-planned adobe wall of the appropriate thickness is very effective at controlling inside temperature through the wide daily fluctuations typical of desert climates, a factor which has contributed to its longevity as a building material. Thermodynamic material properties have significant variation in the literature. Some experiments suggest that the standard consideration of conductivity is not adequate for this material, as its main thermodynamic property is inertia, and conclude that experimental tests should be performed over a longer period of time than usual, preferably with changing thermal jumps. Poured and puddled adobe, puddled clay, piled earth, today called cob, is made by placing soft adobe in layers rather than by making individual dried bricks or using a form. Puddle is a general term for a clay or clay and sand based material worked into a dense plastic state. These are the oldest methods of building with adobe in the Americas until holes in the ground were used as forms, and later wooden forms used to make individual bricks were introduced by the Spanish. Bricks made from adobe are usually made by pressing the mud mixture into an open timber frame. In North America, the brick is typically about 25 by 36 centimeters in size. The mixture is molded into the frame, which is removed after initial setting. After drying for a few hours, the bricks are turned on edge to finish drying. Slow drying in shade reduces cracking. The same mixture without straw is used to make mortar and often plaster on interior and exterior walls. Some cultures use lime-based cement for the plaster to protect against rain damage. Depending on the form into which the mixture is pressed, adobe can encompass nearly any shape or size, provided drying is even, and the mixture includes reinforcement for larger bricks. Reinforcement can include manure, straw, cement, rebar, or wooden posts. Straw, cement, or manure added to a standard adobe mixture can produce a stronger, more crack-resistant brick. A test is done on the soil content first. To do so, a sample of the soil is mixed into a clear container with some water, creating an almost completely saturated liquid. The container is shaken vigorously for 1 minute. It is then allowed to settle for a day until the soil has settled into layers. Heavier particles settle out first, sand above, silt above that, and very fine clay and organic matter will stay in suspension for days. After the water is cleared, percentages of the various particles can be determined. 50 to 60% sand and 35 to 40% clay will yield strong bricks. The Cooperative State Research, Education, and Extension Service at New Mexico State University recommends a mix of not more than a third clay, not less than half sand, and never more than a third silt. During the Great Depression, designer and builder Hugh W. Comstock used cheaper materials and made a specialized adobe brick called bit adobe. His first adobe house was built in 1936. In 1948, he published the book Post Adobe, Simplified Adobe Construction, combining a rugged timber frame and modern stabilized adobe, which described his method of construction, including how to make bit adobe. In 1938, he served as an advisor to the architects Franklin and Kump Associates, who built the Carmel High School, which used his post adobe system. The ground supporting an adobe structure should be compressed, as the weight of adobe wall is significant and foundation settling may cause cracking of the wall. Footing depth is to be below the ground frost level. The footing and stem wall are commonly 24 and 14 inches thick, respectively. Modern construction codes call for the use of reinforcing steel in the footing and stem wall. Adobe bricks are laid by course. Adobe walls usually never rise above 2 stories, as they are load-bearing, and adobe has low structural strength. When creating window and door openings, a lintel is placed on top of the opening to support the bricks above. Atop the last course of brick, bond beams made of heavy wood beams or modern reinforced concrete are laid to provide a horizontal bearing plate for the roof beams and to redistribute lateral earthquake loads to shear walls, more able to carry the forces. To protect the interior and exterior adobe walls, finishes such as mud plaster, whitewash, or stucco can be applied. These protect the adobe wall from water damage, but need to be reapplied periodically. Alternatively, the walls can be finished with other non-traditional plasters that provide longer protection. Bricks made with stabilized adobe generally do not need protection of plasters. The traditional adobe roof has been constructed using a mixture of soil or clay, water, sand, and organic materials. The mixture was then formed and pressed into wood forms, producing rows of dried earth bricks that would then be laid across a support structure of wood and plastered into place with more adobe. Depending on the materials available, a roof may be assembled using wood or metal beams to create a framework to begin layering adobe bricks. Depending on the thickness of the adobe bricks, the framework has been preformed using a steel framing and a layering of metal fencing or wiring over the framework to allow an even load as masses of adobe are spread across the metal fencing like cob and allowed to air dry accordingly. This method was demonstrated with an adobe blend heavily impregnated with cement to allow even drying and prevent cracking. The more traditional flat adobe roofs are functional only in dry climates that are not exposed to snow loads. The heaviest wooden beams, called vigas, lie atop the walls. Across the vigas lie smaller members called latillas, and upon those brush is then laid. Finally, the adobe layer is applied. To construct a flat adobe roof, beams of wood were laid to span the building, the ends of which were attached to the tops of the walls. Once the vigas, latillas, and brush are laid, adobe bricks are placed. An adobe roof is often laid with bricks slightly larger in width to ensure a greater expanse is covered when placing the bricks onto the roof. Following each individual brick should be a layer of adobe mortar, recommended to be at least 25 millimeters thick, to make certain there is ample strength between the brick's edges and also to provide a relative moisture barrier during rain. Roof design evolved around 1850 in the American Southwest. 3 inches of adobe mud was applied on top of the latillas, then 18 inches of dry adobe dirt applied to the roof. The dirt was contoured into a low slope to a downspout, aka a canal. When moisture was applied to the roof, the clay particles expanded to create a waterproof membrane. Once a year, it was necessary to pull the weeds from the roof and reslope the dirt as needed. Depending on the materials, adobe roofs can be inherently fireproof. The construction of a chimney can greatly influence the construction of the roof supports, creating an extra need for care in choosing the materials. The builders can make an adobe chimney by stacking simple adobe bricks in a similar fashion as the surrounding walls. In 1927, the Uniform Building Code, UBC, was adopted in the United States. Local ordinances referencing the UBC added requirements to building with adobe. These included restriction of building height of adobe structures to 1 story, requirements for adobe mix, compressive and shear strength, and new requirements which stated that every building shall be designed to withstand seismic activity, specifically lateral forces. By the 1980s, however, seismic-related changes in the California Building Code effectively ended solid wall adobe construction in California. However, post and beam adobe and veneers are still being used.